Displacement relation in a progressive wave. To describe the propagation of a wave in a medium, we need a function that completely gives the shape of the wave at every instant of time. For example, the wave on a string. As shown in the diagram, we require a relation which describes the displacement of an element at a particular position as a function of time, and also describes the state of vibration of various elements of the string along its length at a given instant of time. For a sinusoidal wave, this function should be periodic in space as well as in time. And let y, a function of x and t, denotes the transverse displacement of the element at position x at any time t. As the wave sweeps through succeeding elements of the string, the elements oscillate parallel to the y-axis. And at any time t, the displacement y of the element at a position x is given by y xt equals to a sine kx minus omega t plus phi. This function is periodic in position, coordinate x and time t. It represents a transverse wave moving along the x-axis and represents a progressive wave traveling along the positive direction of x-axis. On the other hand, a function y equals to a sine kx plus omega t plus phi represents a wave traveling in the negative direction of x-axis. The set of four parameters a, phi, k and omega represented in equations 1 and 2 completely describe a harmonic wave. Here, y, a function of x and t, represents the displacement, a denotes amplitude, and kx minus omega t plus phi denotes phase, where k is the angular wave number, omega angular frequency, and phi initial phase. To understand the definition of the quantities in equation 1 and 2, consider the graphs shown here. These graphs represent plots of equation 1 and 2 for 5 different values of time t as the wave travels in positive direction of x-axis. A point of maximum positive displacement in a wave shown by the arrow is called crest, and a point of maximum negative displacement is called trough. The progress of the wave is indicated by the progress of the short arrow pointing to a crest of the wave towards the right. As we move from one plot to another, the short arrow moves to the right with the wave shape, but the string moves only parallel to y-axis. And as we go from the plot A to E, a particular element of the string has undergone one complete cycle of changes or completed one full oscillation. And during this course of time, the short arrow head or the wave has moved by a characteristic distance along the x-axis. Amplitude of a wave is the magnitude of the maximum displacement of the elements from their equilibrium positions as the wave passes through them, as shown in figure A. Since A is only the magnitude, it is a positive quantity even if the displacement is negative. And the phase of the wave is the argument kx minus omega t plus phi, of the oscillatory term sin kx minus omega t plus phi in equations 1 and 2. It describes the state of motion as the wave sweeps through a string element at a particular position x. It changes linearly with time t, and the sine function changes with time, oscillating between +1 and -1. So its extreme positive value +1 corresponding to a peak of the wave moving through the element. Then the value of y at position x is A, the amplitude. Its extreme negative value -1 corresponds to a value of the wave moving through the element. Then the value of y at the position x will be -a. Thus, the sine function in the time-dependent phase of a wave corresponds to the oscillation of a string element, and the amplitude of the wave determines the extremes of the element's displacement. The constant phi is called the initial phase angle, and the value of phi is determined by the initial time t is equals to 0 and velocity of the element, say at x is equals to 0. Wavelength and angular wave number. Wavelength is denoted by lambda of a wave is the distance between the consecutive repetitions of the shape of the wave. It is the minimum distance between two consecutive troughs or crusts. A typical wavelength is marked in figure A, which is a plot of equation 2 for time t is equals to 0 and phi is equals to 0. So by putting the value of t and phi 0 in equation 2, you will get yx 0 is equals to a sine kx. And by the definition, the displacement y is same at both ends of this wavelength. That is, at x is equals to x1 and at x is equals to x1 plus lambda. From equation 2, you will get a sine kx1 equals to a sine kx1 plus k lambda. And this equation will be satisfied only when k lambda will be equals to 2 and pi, where the value of n varies from 1, 2, 3 and so on. Since lambda is the least distance between points with the same phase, so n is equals to 1 means k is equals to 2 pi upon lambda and is called angular wave number or the propagation constant, and its SI unit is radian per meter